So now we're going to think about slope in a different way. If we go back to the definition of velocity, average velocity is displacement over the time interval. And we use that if you had sections of constant velocity we used slope on a position versus time graph to find that average velocity. So velocity was the slope of a position graph. We now want to start talking about instantaneous velocity. Instantaneous velocity, velocity is velocity right now. If you go on a long trip, you can say, hey, it took us 5 hours to get to Dallas, which is 250 miles away, so we had an average velocity of 50 miles per hour. Now, that includes the times where you're going much faster, hopefully not too high above the speed limit, and the time you got stuck in traffic. So your speedometer may or may not ever have read 50 miles per hour, but that would be your average velocity for the whole trip. Instant velocity is approximately what your speedometer reads. Honestly and truly, it's not. That's still an average velocity. It's just over a shorter time, but let's go with it. So instantaneous velocity is, I'm going to measure this velocity over a shorter and shorter and shorter and shorter and shorter and shorter time. So we write that mathematically is that V, instantaneous, so no subscript, is the limit. Now you can read this as delta t goes to 0, but this means the limit as I use a smaller and smaller time interval of this function, and this turns into the derivative, our purpose today. So the derivative of the position function is the velocity, and velocity is slope. So we are functionally writing out information about how to calculate slope. So I have some graphs, and because I pre-made them so that they'll look good, because you can imagine me trying to draw that specific a graph like that. So you can see this is a position versus time graph. I've given you the points here. And the important thing I want you to notice about this is it's an undercurve. This is not an object traveling at a constant velocity. Now we could calculate the average velocity for the whole trip. Average velocity is 80 meters over 4 seconds. So this is 20 meters per second. But this car was going much slower and eventually much faster. So at different times was going different speeds. So we're going to calculate the slope at each point of these 4 seconds to find the instantaneous velocity. You did this with the physics aviary lab a little bit yesterday. So at 1 second, if I draw a dot there, I have a ruler, and I need to find the tangent line like you did in the physics aviary experiment. So I'm just looking to look at this part of the graph, and I'm trying to get my ruler parallel to that line. So I'm only touching at one point, and I can draw on a line. And I know if I need slope, I need to have 2 points. So I know at 1 second, we were at 5 meters. And for my second point, at half a second, I was at 0 meters. So when I calculate the slope, subtract the y's, 5 minus 0, subtract the x's, 1 minus 0.5. 5 divided by 0.5 is 10. So slide the notebook up a little bit. Down here at 1 second, I was traveling at 10 meters per second. If I go to 2 seconds on my position graph, and again, I just look right around it, how do I get my ruler parallel to that curve? So I need to calculate the slope of this new line. So here we have 220, and it crosses here at 1. So this is 1, 0. So the y's, 20 minus 0, over the x's, 2 minus 1, and we get a slope of 20. So down here at 2 seconds, our velocity was 20 meters per second. And if I go to 3, pretty good tangent line. So I know it's 3 and 45, and that's supposed to cross at 1.5. Let's pretend it did. And so 45 minus 0, 3 minus 1.5, 45 divided by 1.5 is 30. So you probably noticed a pattern developing. I'm just going to finish the pattern. This would be 40. I'm not actually going to draw that one. Also, back at 0, if I hold my line to get it parallel, it's pretty much flat. That was a velocity of 0. So now I can graph these velocities. So 0, 10, 20, 30, 40. And that is a very obviously straight line. So this person, however they were driving, was increasing its speed at a very steady rate. We have a constant increase in velocity here. So now we're going to talk about functions. This function is easy. The velocity is a function of time. 10, 20, 30, 40. So it's 10 times the time. 1 times 10, 2 times 10, 3 times 10, 4 times 10. So this function is 10t. The position functional is a little harder. But if you look at these numbers, if you take 5 out, factor 5, divide by 5 is 1, divide by 5 is 4, divide by 5 is 9, divide by 5 is 16. And you should recognize these as the squares. So the x of t function, I forgot to write my function notation, is 5 times t squared. So I have a parabola here. It turns out it's exactly a parabola. And then my velocity function ended up being a straight line. So now I'm going to skip months of calculus, and you are allowed to use the shortcut to check your work in calculus for those of you in that course, but you are not allowed to use it as justification until Mr. Lee teaches it to you. So if we go down here, if you have a position function that is of this general form, so you have some kind of coefficient and then t to some exponent, because t is our variable. So a is a constant in front, the coefficient, n is the power of t. Then your derivative, the velocity is the derivative of the position function. You multiply the constant and the exponent, so you do n times a. And then you lower the power by 1, so n minus 1. So if we use our two, they're just barely on the screen. Our example here, x is 5t squared. X of t, shame on me. Therefore, v of t, I multiply my exponent and my coefficient, so 2 times 5, times t to the lower the power by 1 value, so 2 minus 1. Now we'd of course simplify this. 2 times 5 is 10, and t to the 2 minus 1 is 1. Well, anything to the first power is itself. So finally, we'd actually enter this in the Schoology assignment tomorrow as v of t equals 10t. Okay, acceleration. You know average acceleration is the rate of change of velocity. So you can guess that the instantaneous acceleration is the derivative of the velocity. But velocity is the derivative of the position, so acceleration is also the second derivative of time, of position. Oh my gosh. Acceleration is the second derivative of position. So second derivative means just do the derivative twice. So if I give you position and I ask you for velocity, you do the derivative formula once. If I give you position and ask you for acceleration, you do the derivative once to get velocity, you do it a second time to get acceleration. So I have one more example. Let me turn the page. And this one's a little bit longer on purpose. So x of t equals 3t to the 4th minus 3t plus 7. And I first want to know v of t, and eventually I want to know a of t. So I need to do the derivative, dx dt. And let me write the formula back on this page. If x of t is a t to the n, then v of t equals n times a t to the n minus 1. So we multiply the exponent times the coefficient, so 4 times 3, and we lower the power, so t to the 4 minus 1. Then we go to the next one. This coefficient is negative 3. Don't think of it as subtracting 3. So this doesn't have an exponent on it. It does. It's an implied 1. So I'm going to draw the 1 in there. So 1 times negative 3, or minus 1 times 3, times t to the 1 minus 1. And then 7 doesn't have a t at all. Well, we can write t in an interesting way. We can add to this t to the 0 power, because you know anything raised to the 0 power is 1. So then our derivative here would be 0 times 7 times t to the 0 minus 1. So now we simplify. 4 times 3 is 12. T to the 4 minus 1 is 3rd. Minus 1 times 3 is 3. T to the 1 minus 1 is 0. Plus 0 times whatever is just 0. And finally I clean this up. 12t cubed minus 3. T to the 0 is just 1. So it goes away, and then plus 0. Why would you write that? So if this was your Schoology question, the original one here, then there's your velocity function. Now if I want to know the acceleration function, I've got to do the second derivative of position or the first derivative of velocity. Well, we already did the velocity. So to find the acceleration, we just do it again. So same formula, exponent times coefficient, 3 times 12, t to the 3 minus 1, minus 3, well, let's put back in this version, 3 t to the 0, so times 0, t to the 0 minus 1. So this is 36t squared minus 0, or 36t squared. So I want to write the three equations, three functions together. Our original x of t, 3t to the 4th minus 3t plus 7. V of t, 12t cubed minus 3. And a of t, 36t squared. So notice that the leading or the greatest exponent has decreased by 1 each time. Also, some of the terms drop away, so there are often fewer and fewer terms. And this is a pretty complicated position function, and so also velocity and acceleration. But if we go back to the first page and now do our acceleration function from this one, our acceleration would be 10 times t to the first. This is just an acceleration of 10. So we have a constant acceleration. It's not varying with time. And that's exactly what we saw here, a constant increase in velocity because it's a constant acceleration. It's going to be good.